Today we'll be exploring a crucial concept in financial modeling, the arch effect, and its profound implications for analyzing time series data. This particular topic will be the central focus of our entire discussion throughout this session. To begin, we'll demonstrate this concept practically. We'll utilize the Finance Research Gate website, a valuable resource, to select a relevant example and illustrate how these principles work in real-world scenarios. So the very first thing I'm going to do is select the appropriate time series. And then make your daily selection. Regarding the frequency, I will then proceed to begin a specific analysis. For instance, I'll initiate this particular examination right here, starting from the year 2000 and concluding precisely in 2005. And then we proceed to select Apply to make it appear on the screen. The main variable of interest we'll be examining is the daily return, and for the purpose of this analysis, we're going to focus on just one firm. To illustrate, let's pick a well-known company, Microsoft. So to begin, within the designated search field for tickers, you'll need to carefully input the specific stock symbol for Microsoft. Once that's done, simply press the Enter key on your keyboard, and then proceed to click your mouse cursor anywhere outside of that input box. That will effectively restrict the available tickers to only those within our search ticker. And then moving to the left side of the interface, we can clearly see our specifically targeted firm, which is Microsoft. Following that, we proceed to select the Apply Filters option, which then meticulously applies the previously selected metric directly to our current firm selection. In this particular instance, we're focusing on just one single firm. It will take a moment for me to fully process that. If you take a look just below, you'll find we presented a comprehensive chart illustrating Microsoft's daily stock returns, covering the period from the year 2000 up to 2005. This visualization can be easily enlarged for a closer, more detailed view of the data. Additionally, we've provided you with the convenient option to download this image directly to your device. To do this, for instance, you would simply locate and select the three small dots and then proceed to click the Save button. From this point, we have the ability to enlarge the display, allowing us to clearly observe the chart. Now, the mean return may be constant over time, but clearly in this chart we have something that is varying over time. It's not the actual return that's the main concern, but rather the unpredictable volatility of those returns. And this precisely is the reason we devote our attention to the ARCH model. With ARCH, what we're essentially doing is systematically modeling how that volatility changes throughout time. When a period of past volatility, for instance, a time of high market fluctuations, is then followed by another similar period of high volatility, and conversely, when a calm, low volatility period is succeeded by another low volatility period, this phenomenon indicates what we call volatility clustering. So what we observe is that the volatility in this context is not a fixed value. Instead, it's a dynamic process, constantly evolving, and its current state is directly influenced by previous periods of volatility or by the impact of prior error shocks. In this particular situation, we observe that the variance is not constant, which is a key characteristic. However, this non-constant variance can indeed be effectively modeled. Specifically, we can employ the ARCH model, a powerful tool designed to help us thoroughly understand and accurately explain the projected future variance associated with our primary variable of interest. When we examine the visual representations of the data, specifically for Microsoft, it becomes immediately clear that both the phenomenon of volatility clustering and the presence of heteroscedasticity are quite obvious. You'll notice that it's not always a constant value. For instance, if we look at this particular section, the market volatility is notably high, and this phenomenon tends to occur in distinct clusters, which means that periods of elevated volatility are typically followed by or closely accompanied by other periods that also exhibit high volatility. Whereas if we examine this other section, we clearly observe much lower levels of volatility, and these calmer periods also tend to cluster together within the same general time frame.
So the arch that we're talking about here refers to
the term autoregressive describes a model where the output depends on its own prior values. The A specifically stands for autoregressive. You see, the particular component is the autoregressive part, meaning it relies on its own past values. And the C here is entirely conditional. And this letter H in this context specifically refers to the concept of heteroscedasticity.
For example, the initial step when applying the ARC model involves identifying a suitable framework capable of explaining our variable of interest, which in this case is the daily return. For this purpose, we will be utilizing the simple mean model. So the mean value is typically considered the best predictor for the expected return. Now, the difference between the actual observed return and that mean value will then provide us with what we define as the error term. This resulting error term is then assumed to follow a specific mathematical function. So, in this specific context, the symbol sigma is used to represent the standard deviation. As for z, it represents the innovation, which can also be thought of as the driving noise that influences the overall process. Crucially, this innovation, z, is characterized by having a mean value of 0, and its variance is exactly 1, meaning it has unit variance. So, the ET, or perhaps more clearly, the error term we're discussing here, represents the actual shock observed in the return data. Meanwhile, z, on the other hand, signifies the shock that remains after we have carefully removed the effects of volatility. Essentially, it's a standardized measure of that return shock. So, in this particular instance, the symbol z is used to denote the observed actual return shock, which is then precisely divided by the calculated standard deviation of those returns. This is the precise reason why we need to multiply our standardized variable z by the standard deviation sigma at this point in our calculation. By doing so, it's as if we are effectively canceling out certain components, which then allows us to isolate and accurately determine the true underlying return shock. What exactly is the central idea being presented here? His crucial insight is that the variance of these particular shocks is not a static value, but rather it's a function that depends on the parameter t. Consequently, the volatility, or the underlying variance, is continuously shifting through time. And furthermore, it's also determined by the impact of all the previous error shocks. Therefore, we are able to model the statistical variance, or perhaps the overall volatility, as a direct function of those previous error shocks. Specifically, we consider 1 period prior, 2 periods, 3 periods, extending up to q periods. This is a situation where a more recent shock has a significantly greater impact compared to a shock that occurred further in the past. Please note that within this particular model, the total sum of all the coefficients, and indeed each individual coefficient, must be strictly greater than 0. This is essential so that we can confidently guarantee that the resulting variance will always be positive. Furthermore, the aggregate sum of these specific coefficients cannot be significantly large, which is crucial because it enables us to obtain a more constrained and well-defined solution for the anticipated volatility. Within the framework of this particular model, we observe a clear relationship. If the magnitude of the recent error shock is substantial, then the overall variance within the system will consequently increase significantly. Conversely, if the impact of these recent shocks is rather low, then this will effectively drive down the overall level of volatility. Though, the volatility that we are observing here can be accurately interpreted as the cumulative effect of all preceding shocks. Furthermore, should a new shock of considerable magnitude arise, it will cause the variance to significantly increase, and the inverse holds true. Though, this particular framework we're examining right now is what we refer to as the arch model. Yes, this is precisely the arch model, a key concept in our analysis. And the null hypothesis we are considering here states quite clearly that this specific type of influence where past shocks affect the variance simply does not exist or is not present in our data. So, our null hypothesis is that the coefficients alpha 1 through to alpha q are all equal to 0. This essentially means that the variance remains constant, and it does not depend on any of the past error shocks. The alternative hypothesis states that, when considered collectively, these values are not equal to 0. This is precisely why we then introduce the ARC-LM test statistics, which is also known as the Lagrange multiplier. The Lagrange multiplier, in its essence, is simply equivalent to the R-squared value of this particular model. This value is then multiplied by t, where t specifically represents the total number of observations that we are utilizing to conduct this entire regression analysis. So, a higher R-squared value indicates a strong likelihood that we can confidently reject the null hypothesis. This allows us to accept the idea that previous shocks or innovations are indeed significant factors driving the observed volatility in the system as time progresses. That test statistics themselves, such as the Lagrange multiplier, LM test, and the Lagrange multiplier, ARC-LM test, are designed to follow a chi-squared distribution. This is fundamentally because the underlying formulation and calculation are directly derived from the R-squared statistic. Therefore, when we utilize a squared term for our test statistics, we then adhere to the chi-squared distribution possessing a specific number of degrees of freedom, which is equivalent to Q. Here, Q, as previously mentioned, represents the total number of past shocks that we incorporate into our model. If the p-value is statistically significant, which means it's less than 5%, then we would reject the null hypothesis and consequently accept the presence of the arc effect. For instance, let's consider a practical numerical example. Imagine that from our analysis of the daily financial returns, we were able to precisely identify and calculate the specific errors observed in each individual period. First, we take these calculated errors and square them, and subsequently, we perform a regression analysis on these resultant squared error values, using the previously observed squared errors as our independent variables, all while carefully applying the principles of the ARCH model. So, for instance, what we're looking at here is the most recent error shock that occurred within this specific period. To analyze this, we then regress that against the error shock from the previous time lag and also the error shock from 2 time lags ago, and so forth. So, to put it simply, we're working with our dependent variable y and our independent variables x1 and x2. We then perform a straightforward regression analysis using these. After running the regression, we determine the r-squared value. Following that, we take this r-squared value and multiply it by t. For this particular scenario, we utilize 6 distinct observations when conducting our regression analysis, which ultimately gives us a result of 6. If we take the value of 6 and multiply it by the r-squared value that we obtain, this calculation will then provide us with the LM statistics. If this value is quite large and also statistically significant, it indicates the presence of an arch effect, meaning that previous error shocks were already determined and possess the ability to influence the current level of volatility. Usually, we can observe how volatility tends to cluster together. This indicates that the volatility itself is dynamic and constantly shifting. It also appears that previous periods of market activity significantly influence the current level of volatility. Now, if you wish to conduct a test for that particular aspect utilizing the ARCH-LM methodology, then as we proceed to scroll further down, you will observe that in this specific section, we have the ARCH-LM test readily available. We have a very significant value here. The actual statistical figure itself is exactly 101. The p-value is exceedingly small, indeed it's practically zero, which strongly suggests that the probability of observing this particular test statistic as a member of the chi-squared distribution that is derived under the assumption of the null hypothesis that there is absolutely no arch effect present is in fact extremely minute. What this means is that we hold a strong conviction that daily stock return performance of Microsoft Corporation demonstrates a level of volatility that is not constant, but rather changes and evolves over time. This particular measure of variability, whether we call it volatility or its statistical variance, is fundamentally determined by and can be understood as a direct function of the prior period's unexpected errors or new innovations. Because the p-value that we've observed in this particular instance is less than 5%. And here we are provided with the crucial option to accurately determine the optimal number of lags. So the question is, how many previous error terms do you wish to incorporate into your ARCH model? Typically, the standard setting for this, especially when dealing with daily data, is set at 12. However, you certainly have the flexibility to either increase that number or conversely to reduce it. As an illustration, consider a scenario where you might decide to bring that value down to just 4. Consequently, the calculated test statistics will be different, as well as the p-value.
It's going to require a significant amount of time to execute the ARCH model and then meticulously compute all the relevant LM statistics. We're at 45 now and it's still showing as significant.
Therefore, this analysis will effectively support our primary conclusion, indicating that we are indeed observing both volatility changes and distinct volatility clustering patterns for the particular firm we have chosen. That concludes our presentation for today. We sincerely appreciate your time and attention.